Thank you for joining me today. My name is Alicia Henn. I'm Chief Scientific Officer for BioSpherix. And this webinar today is talking about taking the cytocentric approach to avoiding suboptimal transients for the patient in the incubator. So I'm going to start us off today by asking you to do something a little different, which is to close your eyes and mentally stand in the doorway of your laboratory. This might be particularly helpful for those of us that might be at home while we are weathering the latest coronavirus outbreak. But even if you're in your office, I want you to mentally stand in the doorway of the lab and look around at what you see inside. What do you see? You see chairs, you see tables, you see benches. Okay, open your eyes, come back to me. I'm going to ask you, what in your facility, what did you see there that is actually designed for the needs of cells rather than for the needs of the people that work in the laboratory? A lot of you might have thought of this, your traditional room air cell culture incubator. It seems like it's set up for the needs of the cells, but really when you think about it, it's designed for the needs of the people in the lab more than the needs for cells. I mean, it's easy to get your hands in there. It's easy to get your face right in there. But we all know that this is a terrible environment for cells. It's got that big pan of water in the bottom, which is always contaminated. Every time you open the door, all the gas levels change. So the CO2 drops, the oxygen goes up, and the oxygen levels inside that room air incubator are lower than room air, but they're not as low as they need to be for cells that come from inside the body. So it's a hyperoxic environment for cells. And it's a highly variable environment for cells, because whether it's you accessing your cells or it's someone else accessing their cells, it's always changing. At BioSpherix, we take what we call a cytocentric approach to providing the best environment for cells in the laboratory. And a cytocentric environment for incubation is one that opens only into a closed cell handling space. The environment here is constantly HEPA filtered for sterility, so it's a low risk of contamination inside this environment. The air is constantly warm to 37 degrees. And you can set it for physiologically relevant conditions because there's only tanked gases in this space. So oxygen, CO2, nitrogen, you can dial in the proper atmosphere for cells for this cell handling space. And it's closed. It's closed off from room air, so it's closed off from all that variability that comes with doors opening into a room air space. Now, when cells need to be handled, you need to change the medium, you need to do your regular cell passaging. The environment's even worse for them. This is even a more people-centric environment for cells. It's easy for people to put their hands into a biological safety cabinet. It's easy to handle the cells there, but their risk of contamination is highest there for the cells when you think of it from the cell's point of view. Not only are they hyperoxic, and they're hypocapnic, there's not enough CO2 there, but now they're freezing. This is a cold environment for cells, and it's very stressful. A cytocentric cell handling space is closed off from room air. We have that full control of the gas mixture, so the cells are never in suboptimal oxygen, never suboptimal CO2, and it's warm to 37 degrees. Even the floor is warm to 37 degrees. So the cells are never cold. They're never hypothermic. So you get a much more consistent environment for them. You don't have all this variability when they're exposed to the room air for cell handling. So in reducing variability for cell processing, a lot of people are turning to automation. Particularly if you have a high throughput application, you're going to need some automation in your processing. But taking this machinery and putting it in a people-centric environment now makes that a very stressful environment for cells. Because not only your gas level's off, your temperature is off, but the cells also have to deal with any particles that are being generated by machinery as well. That could be a threat to them. So this is the wrong approach to reducing variability for cell processing. We can take any type of automation and put it into an essentially cytocentric environment. So the gas levels are at the proper levels for cells. The temperature is controlled. We don't let the temperature go too high because machinery can add heat to that same environment as well. And we keep the particles under control so the particles aren't a threat to the cells in that process. We can include any type of equipment that you would need inside the cytocentric space for the cells to reduce the risk to them, whether it's a microscope or a centrifuge or a bioprinter or any type of cell encapsulation or cell packaging equipment, you name it, we can put it inside a closed environment, a safer environment for the cells. More broadly, the ex vivo system protects an entire process, start to finish. So when the cells come into your lab, they go straight into the ex vivo, whether that's as a tissue, as in this case. This system was made for isolating pancreatic islets for a process that's being done in Australia, and these islets are then sent all over the continent for clinical trials. So in this case, the tissue comes into the ex vivo on the left-hand side in the laminar flow hood where the operator's working there right now, and then they go through the system as they're processed. And inside you have incubators, that's what those black doors are. On the left, you have chilled chambers for processing at cold temperatures. There's a huge floor-standing incubator on the far right. They have hanging bars in there for hanging fluids. They have magnetic plates for hanging up tools. Everything that they need for processing those islets is inside the ex vivo, and so that it's in a controlled, completely controlled environment for the entire process, start to finish. And when the cells leave the ex vivo, they're ready to leave the laboratory. We've also enclosed huge pipetting robots like this TCAN robot that you see on the left. That one is at Cleveland Clinic. On the right-hand side, you see large doors that we made to accommodate bioreactors made for full human lungs. This is for a decell recell process for whole human lungs. So you bring us your process and we can enclose it in the proper environment for the cells and tissues. One of the most useful aspects of our approach is that our systems are all modular. So you can start small when your process is not locked down yet in the laboratory, and you can get a small system and identify the best conditions for your cells or tissues for each part of your process. And then as you get more funding, as your process develops, as you move toward clinic, you can add on modules, you can bring in more equipment, you can bring in automation, and you can reuse the same modules that you started with over and over to redesign your system as your process grows, until at the end you have a fully GMP compliant cell production factory using the same modules that you started with. This means that your conditions don't have to change all the way through. You have much less in the way of tech transfer risk as you move toward clinical trial because you have the same environment. All of these parameters are monitored full-time, 24/7 in each module independently. Oxygen, CO2, humidity. We have limit controls on things like disinfectant fumes. We have limit controls on particles. And of course, temperature of the floor and temperature of the atmosphere are monitored continuously. It's full-time ISO 5 conditions. There's no room air inside, so this gives you far more control and far more reproducibility over your process. Because when you look at the conditions that cells actually endure in an open room laboratory, every time they come out of the incubator, of course, we know that the CO2 goes off, and that makes the pH goes off, and the temperature, of course, goes off, and we know that the oxygen levels are never really optimal in a room air situation for cells. So cells actually spend far more time in suboptimal conditions than they do in optimal conditions. And even in the pinnacle of the highest technology we have for processing cells, the cleanest clean room in the world, you still have the same sources of variability that go into the most rudimentary of cell culture labs anywhere in the world when you're exposing these cells to room air conditions. And in a clean room, because people have to wear so many layers of garb, they often keep them really cold, and that's even worse for the cells. So this is the ultimate in people-centric environment, not a cytocentric environment. A cytocentric environment has full-time optimal conditions no matter where the cells need to be. It's better for the cells, and it's closed off from all the variability that comes with room air exposures. There's no mixing of the room air with the cell or tissue environment because all the gases inside the ex vivo come from tanks, and also any gases that leave the ex vivo can be pumped away, vacuumed away, and sent to a distant location. So this is an enhancement of biosafety as well. This is better safety for the technicians in the lab, the people there, as well as better for the cells. We also have a solution for transport in between ex vivo systems. If you need to divide your process among different systems, we have a transport chamber that will maintain the conditions around these cells while you transport in between ex vivos. So what's it matter to the cells? Let's talk about cytocentric. Let's talk about what we can see back from the cells. It doesn't matter that they have full-time control of conditions or not. Well, we have data using from human bone marrow MSC, mesenchymal stromal or stem cells, that shows that when you keep them in full-time controlled oxygen, in this case 5% oxygen, as compared to traditional cell culture room air, that's the blue line. These are cell coverage traces from the Cytosmart microscope coming up from freeze. You can see that even coming up from freeze, the cells are growing much, much better in full-time controlled oxygen than in traditional cell culture room air. We also get more passages out of them. They grow consistently better over time when you control the oxygen to physiologic levels. So what if I have something like a tri-gas incubator where I can control the oxygen during incubation and just take them out to the biological safety cabinet, handle them real quick, get them right back in the incubator? That's good enough, right? Well, not really. We've shown that this part-time oxygen control is not as good as full-time oxygen control for cell growth. Again, these are, cell traces using the Cytosmart microscope. You can see that when cells are exposed to room air conditions for cell handling, it does affect their growth over time. We see this also when we look at the videos of the of individual cell fields over time. This was data from a poor summer student that had to sit down and do frame by frame cell analysis, looking at the fate of every cell in every field from the videos, from the Cytosmart videos. And what we found was that if cells are exposed to room air for medium changes and for cell passaging, that we can see that cells are far more likely to never divide again. This is true in both early passages and in late passages for human bone marrow MSC. So really, full-time controlled oxygen is much, much better for these cells. But it doesn't take that long. You say it's just a quick medium change, then they're right back in the incubator. These are things I hear from people all the time. It doesn't matter. But actually, if you look at how long it takes those cells to return to the right oxygen level after they're put back in a low oxygen incubator, you can see that there's lots of time for the cells to be affected by this. Here's the pericellular oxygen in this chart on the left, and you can see that in the headspace or in the medium, it takes almost 2 hours for those cells to get back to the proper oxygen level. after they go back into the incubator. And the inset, of course, you can see that if the cells are never out of optimum, then they never have this time that they have to readjust back to the proper oxygen level. And the intracellular oxygen level, we assayed this using Agilent's intracellular oxygen assay. And the pericellular oxygen over here we did with a simple immersion probe, but this the intracellular oxygen we did with their plate reader based intracellular oxygen assay. And what we found here was that when the cells went back into the incubator, oxygen actually went up for a little while before it started falling. And again, of course, if the cells are never out of optimal conditions, they never experience this swing in conditions. And it takes them almost 3 hours to come back to the proper oxygen levels. Being out of optimum for 2 or 3 hours is a really long amount of time for oxygen because of what we know about hypoxia-induced factor 1 alpha, HIF1 alpha. The Nobel Prize was awarded to the researchers that did the initial work on this. And one of the things that they found, this was from one of the early papers on HIF1 alpha, is that I just want to bring your attention to the bottom, the scale here, the time scale. We're looking at minutes, single minutes for HIF1 alpha to be modulated in response to simple changes in oxygen. And why does that matter? Because downstream of HIF1 alpha are so many single transduction pathways and cell functions that are absolutely critical to the cells that we're taking care of in our cell processing. We're talking about cell metabolism, we're talking about cell division, cell differentiation, cell death. We're talking about mTOR, Notch, VEGF, JAK-STAT. All of these are critical to the function that we want these cells to carry out for us and for our patients after they leave our care. So when we have control of conditions, the oxygen, the CO2, the temperature, the humidity, we can make those now the same run after run, process after process. We can have exactly the same conditions, verifiably the same conditions. And once we have the best conditions, we can then take that process and we can clone that system and clone those conditions and put them anywhere on the planet. So you have verifiably identical conditions, whether your process is in San Diego or in Singapore or on a ship at sea. Because when we talk about trying to improve in vitro reproducibility, we talk a lot about things like reagent identity, we talk about reporting issues, we talk about experimental design, we talk about problems with statistics, we talk about even cell identity. And those things change and come into play to different extents, whether it's one lab trying to reproduce their own experiments, whether it's a collaborator down the hall trying to reproduce your experiments, or whether it's someone halfway around the planet picking up a publication and trying to reproduce your experiments. But there's one factor that goes into every single cell-based process or assay anywhere on the planet, and that's the conditions for the cells, and this is key to every single one. It's critical to take this point of view and change it from a people-centric point of view to a cytocentric point of view. Make the conditions about your cells from start to finish in whatever cell assay or cell process that you have to do for the good of the patient in your incubator. And I'm going to stop talking here, but that doesn't mean the dialogue has to stop. Please feel free to reach out to us, to reach out to me. I'd love to answer your questions and give you more information. Thank you very much.